Okay, so I'll just do a quick reminder of something I said in the end of the previous talk, and then I'll switch to the main topic of the course, which is these complex cells. Okay, but I'll remind you that at the end of the talk, I was talking about the following problem. We have an algebraic curve. It could be an analytic curve, doesn't really matter. And we want to cover it with disks and annuli. And I was claiming that, well, with disks, you are not going to be able to do it uniformly, but if you use annuli as well, then you can do it uniformly. And I was saying that to try to see how the proof works, let's imagine a situation that we have a ramified covering. So our curve looks something like this, or maybe this. So this projection is proper. And then I mark down the singular points, the ramification points of this. So here it would be this one. But maybe let me make it more interesting. I had, I don't know, another one here. And then I'll have one here. So I mark down these ramification points. Let's say sigma in a disk of radius 2 is ramification for this projection. And then I said that if you think about it, whenever you have disks or annulus down here, you can kind of lift it to, you can just invert the map and you will get a map into the curve. So what the problem basically reduces to is that we have such a set, and I want to cover, or let's say I want to find some collection of cells Cj, where every Cj can be some disk, or a puncture disk, or an annulus. So that's my notation for a disk, a puncture disk with a little circle here, or an annulus. And I want two things to happen. I want the union of these Cj's, these cells Cj, to contain the disk of radius 1. And I want the extension. So this is 1. And I want Cj, the 1/2 extension, to be disjoint, or maybe let me say minus sigma here, because I'm not going to cover the actual singular points, because my second condition is that every cell should be disjoint from sigma. Okay, so it means that each of them is disjoint from sigma, and even if you extend it a little bit, it will remain disjoint. So this notation I defined last time. It means if it was a disk, I just double the radius, and if it was an annulus, then I double the outer radius and I half the inner radius. And now it's just a problem in kind of plane geometry. You have a picture like this. We have a disk of radius 2 inside the disk of radius 1, and we have some points. And we are trying to cover the disk of radius 1 without touching the points. So if the 2 points were something like this, then you can probably do it with a few disks. Like you would put a puncture disk here, a puncture disk here. So these are 2 puncture disks. And then this remaining part, I would cover with a few disks, something like this. Okay, so when the points are far away, there's no issue, and we don't see this more delicate hyperbolic obstruction with the annuli. So the interesting thing happens when you consider a degeneration where the ramification points collide. Okay, that's exactly what happens if we consider xy is equal to epsilon. As I took before, if you project it, there will be 2 ramification points, at square root of epsilon and minus square root of epsilon. And then as epsilon goes to 0, they collide. So you have 2 red points here, very close to each other. And if you try to do it like I did it here, it wouldn't work. You would kind of put 2 very small puncture disks, because when you double the radius of the puncture disk, it should not touch the other red point, right? Because it should be disjoint. So we would need 2 of them, and then we would need all the disks that we can put around here should also be very small, because they shouldn't touch the red point. So you would need to put a bunch of small disks here, right? And you see that, as these red points are colliding, you would need more and more disks. So this is kind of why we are not going to be able to do it with only disks. On the other hand, so this is not good, but if you allow an annulus, then the picture is much simpler. Let me make this final picture here. So now I have the 2 points very close by. I can first put one annulus around them. So I can put one annulus like this, and then this whole thing is just one annulus. Okay, so we cover like the majority of the area with just one disk. And if you look inside this little circle, then we are just back to the previous situation. So here I can use a couple of puncture disks and a few more disks to cover the rest. Okay, so with an annulus, you can do it uniformly. You wouldn't need more and more disks. And without an annulus, you would need more and more disks. So you can kind of try as an exercise to convince yourself that whenever you have any set sigma, then you can do such a covering using disks and annuli. And this covering would, the size of the covering would only depend on the size of sigma. And if you don't use annuli, then it would depend also on the geometry of sigma. Okay, so that's how you see why annuli are really needed. And okay, this story of complex cells is trying to just generalize this to arbitrary dimensions. So the claim is that we can somehow generalize annuli and disks to arbitrary dimensional type of structures that we call cells. And then every analytic set you can cover in this uniform way using finitely many of these cells. Okay, so I want to go to the complexes, but let me first talk about the real cells, even though they were mentioned in some of the talks, but I just want to introduce them with a certain notation that will be convenient for me to use. So I'll first use this notation for the more familiar context of real cells. So what is a real cell? I'm going to define real cells. Real cells. So I mean cells like in O minimal geometry. So a real cell, let's say C in R, this is just a point or an interval. You can think about open intervals. I mean, usually in O minimality people talk about any interval could be open, close, but for me, you might as well think of a point or an interval. And then what is a cell in higher dimension? Let's say we take C in RL. So this is going to be, I'll introduce a certain notation. It's going to be RL plus 1. So I'll define a cell in RL plus 1. It's going to be C 1 up to L times a fiber. And now I'll say what I mean by this special notation. So x1 up to L. Okay, so basically what I want to define is a product, but where the fiber is allowed to move with the base. So C1 up to L is a cell in RL. So just inductively, I take a cell in the first L coordinates, and then this notation C1 up to L O dot F 1 up to L. This just means that I take the points x1 up to L plus 1, where x1 up to L belong to C1 up to L, and xl plus 1 belongs to F evaluated at x1 up to L. Okay, so it's kind of it's a complicated way of writing a very familiar object. Okay, and in order to have L, I want F of x1 up to L to be one of two options. This should be either some point, f of x 1 up to L, or it should be an interval. An interval given by two functions. Okay, where these functions are continuous, where fg from the base cell into R are definable in the structure that you're working with and continuous. Okay, so basically a cell in one dimension, we just take an interval. Dimension, we should fix, let's say, two functions and take whatever is between them. In 3 dimension, we could take something like this, then take two functions and add what's between them, and that's a cell. Okay, so what we want to do is to extend this now to the complex situation, and the intuition is that this is quite similar to annuli in some sense. So, I mean, if you write this out in formulas, this says that the final variable should be between one function and the other function. Right, so if you want to extend this to working, instead of working in R with an ordered field, you want to work in a valued field, you could say that we want the absolute value of the final coordinate to be between the absolute value of two functions. Okay, so you get some annulus. And this will be the definition. Okay, so now I'll basically repeat this with the complex situation. But in the complex situation, there will be some new phenomenon coming from the fact that we can analytically continue things and have this notion of extension, like this little 1/2 that I put there. So it will be a similar picture, but with some variation. Okay, so what is a complex cell? So again, I'll have the base case. So a complex cell C in C1. This will be one of 3, well, even 4 options. So this can be the origin, which I denote by star usually. It's just a point. Or it could be a disk of a certain radius. Or it could be a puncture disk. Or it could be an annulus. Okay, so here we already see a little difference compared to the real situation. So, okay, a point I already had before, right? One of the options was to take, rather than an interval, taking a point. So this is kind of the analog of this thing. But instead of an interval, I now have 3 different options. And the reason is that, you know, in the real setting, an interval is, all intervals are the same. There isn't really a difference between intervals. But if you think about the complex setting, about the structure of the complex manifold, a disk is different than a puncture disk, and a puncture disk is different than an annulus. Okay, so because we're going to use some hyperbolic geometry and some like complex information, we have to distinguish these cases. So it just makes for a little bit more cases, but roughly the idea is the same. Any questions so far? Okay, and now I'll define the general cells in arbitrary dimension just completely analogously. Okay, so I'll repeat it just to make sure we are clear. But if I have a cell in CL+1, I'm just going to define this to be something of the form. So C should be a base cell, 1 up to L, O dot some fiber, evaluated at X 1 up to L, where this C 1 up to L is a subvariety of L, is a cell. So again, by induction. And now this fiber should be one of these types. Okay, so it should be F of X1 up to L should be either or an annulus. Okay, but the first difference. Now I want these, before I said that the radii should be continuous definable functions. But now I'm trying to do everything in a complex setting. It's natural to require that they are actually holomorphic. Okay, so now I want this R1 and R2 to be holomorphic bounded functions on the base. Holomorphic and bounded. That's like this notation.
R?
Yeah, sorry. So either R or R1 and R2 should be holomorphic and bounded. Okay, so this is one difference. Once you say that they're holomorphic and bounded, it kind of means anyway that they are. Okay, I'll say something extra later. Okay, so this is the definition. Is the definition clear? It's hard to write and it's easy to understand. So basically, you start with a disk or annulus, then over every point you put another disk or annulus, but the radii can move holomorphically, and then over every point of that you can fit another disk or annulus and so on. Okay, but the reason that this is a bit different is that we have this notion of extension.
Sorry,
okay.
R1 is always different from 0?
Yeah, sorry. So here, I should have added some conditions. Thank you. So absolute value of R should be greater than 0, or absolute value of R1 should be always less than absolute value of R2, so that everything is well defined.
But A0R is the same thing as D0R, or you want to see them as different things?
Right. Sorry. Well, I mean, it doesn't really, if it's constant 0, then in fact you can just say that this is a this. But yeah, to make things well defined, let's take it like this. Okay, so yeah.
So, but R1, R2 are real functions. Right?
No, sorry. Yeah, so I should have put absolute value. Right, sorry, yeah. Yeah, I'm sorry, I'm mixing up. So in our paper, the notation is already introduced like that, where the annulus of evaluated with complex numbers, you just put the absolute values in the definition. But yeah, I take absolute value. This is important here. So we are working with complex things. We don't have like real radii like we could use there. So now we are putting complex absolute value on everything. Okay, thank you. And okay, so the first main difference is that now we have this notion of extension that didn't really make sense in the real setting. Okay, so I'm going to define a delta extension. And this delta extension, it comes from the same idea that, in this example, I said that I wanted all the disks to extend to twice bigger disks and all the annuli to extend. So we want to kind of keep this in the general case, because that's what allows us to use hyperbolic geometry. We always need our Riemann surface to be in a little bit bigger Riemann surface, and then we can consider this, some abstractions that come from hyperbolic geometry. So what is a delta extension? I'll first define it for the cells. And I, in fact, already defined it for. Is there some question? No. Okay. So I'll define for the cells what a delta extension is. So a delta extension of a disk, this is just going to be a disk of radius r over delta. And the same for a puncture disk. This is going to be the puncture disk of radius r over delta. And then for the annulus r1, r2, the delta extension will be, as I used it before, it will be delta r1 and the r2. Okay, and now I'm going to just inductively extend this to the general case. So I'm going to say that if I have a cell.
Are these open or closed? Or
Always open. Yeah, thank you. It's not crucial because we always have this extension. So really, what happens at the neighborhood is not crucial. But yeah, I take them open always.
Except for the point.
Except for the point, right. And the extension of a point is a point. So yeah, the point is kind of ill-behaved, and I often will ignore it. But yeah, in fact, you should always also allow for the points. Okay, so what is the extension of a general cell? Let's say I have a C1 up to L dot some fiber. Then I'll define the extension delta to be, just by definition, the extension of the base. C1 up to L delta, O dot this F delta. Okay, but you should notice that this definition, it encapsulates some, you cannot always do it. Okay, there is a certain restriction on the cell here, because for a cell to have a delta extension, well, the base should have a delta extension, which I claim is non-trivial, but we would see why it's non-trivial in the next part. But the fiber should also have a delta extension. Now, the fiber is defined by some holomorphic functions on the base. Okay, so in order to be able to define the fiber, you have to be able to analytically continue the functions on the base to the bigger base. Right? We had, in this cell, we had the fiber. It was defined by some radii that are defined here originally. Now we want to extend the cell, so we want this radii to extend to the new bigger base. Okay, so the fact that the cell has this delta extension, it means that all the relevant radii, they can be analytically continued to a little bit bigger domain. Okay, so there's a certain restriction here, and this is why it doesn't really make sense to define this in the real case. I mean, you could stretch your intervals maybe in the real case as well, but in the general real case, you don't have this notion of analytic continuation, so it's not clear if you had a cell and functions on it, and now you increase the base, how would you kind of continue the functions? There must be, you have to do it in some context where you have analytic continuation. Okay, so I'll just mention that, so this requires a R or R1, R2 to this C1 up to L delta extension. Okay, so it's a non-trivial restriction. Okay, is it clear so far? So this is kind of the main definition. This is the complex cells. And now I need, somewhat annoyingly, I need to define one other type of extension. So the thing about these delta extensions is, okay, they're very easy to define with formulas, and they're kind of natural when you're trying to do things like Taylor approximation. So this is kind of the, if you want to estimate the rate of convergence of a Taylor expansion or a Laurent expansion, then this is the right notion to consider. But if you want to do hyperbolic geometry, that's not really the right notion to consider. So I'm going to define one other related type of extension, which is more suitable for doing hyperbolic geometry. And most of what we do is inspired by hyperbolic geometry. So this second type of extension, even though it's less intuitive, maybe it's more inherent to the subject. I'll define a rho extension. It's a very similar definition. It's just numerically slightly different. Okay, so I'll define the rho extensions. And again, I'll define it first for the basic fibers, and then it will extend inductively in the same way. So now, here delta needed to be between 1 and 0, I forgot to say. So this makes sense for delta between 1 and 0, and the smaller delta, the bigger the extension. Now, for rho extension, I'll take rho to be between infinity and 0. And I'll define, for the basic fibers, I'll define this f rho extension. Just a second. I'll define f rho as follows. It will be just the delta extension. And now I'll tell you what delta should be. So, or what rho should be. Rho should be 2 pi delta divided by 1 minus delta square if this fiber f is a disk. And rho should be pi squared divided by 2 log delta if f is a puncture disk or an annulus. And for the point, you don't need to define. The point, the extension of a point is the point anyway. So I introduced this definition. It seems strange. We obviously didn't come up with these numbers randomly. So there's one basic fact that kind of, which is the reason for introducing this definition. So let me write it here. So I'm going to take S, how do I want it? S is a component of the boundary of the fiber. Okay, so for a disk, it would be just the bounding circle, and for an annulus, it would be one of these bounding circles. And the claim is that the length length of S in the extension, okay, in F rho extension is less than or equal to rho. Okay, so in these complexes, we are always going to consider a cell inside the extension. And the idea is that the cell is kind of small with respect to the metric of its extension. Okay, and this is what we will use. So the reason for choosing these particular numbers is that when you do it like that, the length of the boundary is going to be exactly rho, or less than or equal to rho. Okay, so if we have a very small rho, it means that our cell is very short with respect to the hyperbolic metric of its extension. Okay, now after I define it like this for the basic fibers, I'll use the same exact definition to extend. Okay, so now if you have a general cell, I'll just define the rho extension to be the rho extension of the base times the rho extension of the fiber. Okay. Any questions about this? Okay, so I wanted, before going on, I want to draw just a picture of how the annulus looks. So the annulus is the most interesting case of this. And if I could say that the annulus is short, if I could say that instead of saying take a component and say that the length of the component is short, if I could say that just the diameter of S inside the extension is small, then everything would be much simpler. But this is actually not possible. I mean, what we have seen in the previous lecture is that if you take an annulus inside the twice bigger annulus, the diameter of this degenerates. It's not uniformly bounded. It degenerates like log epsilon if the annulus is from epsilon to 1. So it's not true that the size of the cell inside of its extension is bounded. But what is true is that the length of the boundary is bounded. Okay, so this imposes some restrictions on how these complex sets can degenerate in families. They degenerate in a certain way where they might become long in the hyperbolic metric, but you can still find boundary curves that don't become long. So let me just show the picture for the annulus. So I'm going to draw, let's say I'm going to draw a epsilon 1 inside a epsilon over 2, 2. So inside a certain extension, the 2 extension. So it looks like this. I have the whole, and I'm drawing it with respect to the metric of this guy. Okay, so this is a Riemann surface, hyperbolic Riemann surface. It has a metric. With the metric of this guy, it looks something like this. Okay, so this is kind of the boundary. This boundary goes off to infinity. Okay, you have the boundary of the annulus is infinitely far from every point. I mean, this metric is, it's not a bounded metric. But this part, it has these circles are bounded length, bounded, and this is bounded. And this is log epsilon. Okay, so as you decrease epsilon, your annulus sitting inside its extension looks like a tube that's becoming very long, but the sides remain at the same length. Moreover, this part, to make an even better picture, should be like this and this. So this part gets pinched. So this actually tends to 0 as epsilon tends to 0. Okay, so you have a kind of a very peculiar picture where the sides remain at a fixed length, the total diameter, the total length grows, and the length of the, going in the middle gets pinched to 0. And all of these properties are kind of, they manifest themselves in various aspects of complex geometry. So each of these is somehow important somewhere in the proofs. Okay, so that's basically how the picture looks for an annulus. And now when you have an arbitrary dimensional cell, it's consisting of pictures like this, but just kind of composed on each other in several dimensions. So is this clear so far?
Sorry?
Yeah.
So the row extensions are defined only for one-dimensional
No, sorry. So I defined, like for the fibers, I defined a row extension like this, and then I define it for a cell in the same exact way. Like just in so I'll say that the row extension of a cell is just you make a row extension of the base times a row extension of the fiber. So, yeah.
Just a way to fix the size of the extension with respect to
So yeah, it's just a way of fixing it. So it's like just a different choice of delta. I'm saying that I want to choose the delta that will make the length less than rho. But it's just that it behaves asymptotically very different when you're working with annuli or disks. You see, it's kind of a polynomial degeneration for disks, and it's a logarithmic degeneration for annuli and puncture disks. So we have to kind of separate out these cases. Okay, so I want to state the main theorem about complex cells, but for that I will need a few small definitions, so I apologize, bear with me. So the first definition is in order to kind of remedy a certain problem with this analogy with the real case that I've hidden under the rug. So in the real case you have a point, and the point could be, I mean, a cell is any point. Right? Let's say a cell in R could be a point, any point of R. But when I defined the complex cells, I said that it's the origin. Right? Star is the origin. And in the same way, you know, I took a disk, but the disk was around 0. Okay, maybe a better analog in the real case would be a disk that could be shifted to any point. So really, these complex cells, they are not quite like the cells of real geometry. They are like the basic building block, but it should be somehow mapped into the space with certain shifts. So I need to introduce the kind of maps that do this. So I'll make a definition. So a map phi from one cell to another cell is prepared so this is the definition of prepared if it has the following form. If, well, so I'll denote the coordinates. So phi will be phi 1 up to phi L. So these are just the coordinates. And every coordinate takes the following form. J of x1 up to xl. This will be xj to some power, qj, plus some function of the previous coordinates. X1 up to xj minus 1. Okay, and these should be holomorphic and bounded. Okay, so basically we have this triangular shape, and I claim that if you think about what this definition means, it means that the image of a cell, the image of a complex cell, that's more like what we consider to be kind of an analog of a real cell. Okay, so let's say a cell is a point, but when you introduce this map, you could have the point shifted by some function. And then if you have a cell in 2 dimensions, then first you would fix the base, and then in the fiber you have, let's say, a disk, but this disk could be shifted by a function of the base. So that is what allows you to make this translation of the cell. So the image of a complex cell is really kind of what looks like a real cell in the real setting. Okay, so we would, when we are thinking about doing something like cell decomposition, we should be thinking about decomposing a thing as an image of complex cells. Okay, that's similar to how, okay, in my first example, I was saying that I want to cover things by disks and annuli. Of course, it's not this dr and ar, which are always around 0. I wanted shifts of disks and annuli to cover my set, the disk of radius 2 minus sigma or something. So this is kind of the thing that encodes all of these shifts and annuli. Another small difference compared to the real case is that you have these powers here. So in the real case, you can just, you can extract roots because you're working with the interval. It's not a problem to extract a root. But because we are working with puncture disks and annuli, and we want everything to be really holomorphic, not having finite monodromy, then we have to allow this power map. So we have to allow some, so the complex cells, they don't exactly map one-to-one to the space. They kind of cover the space with ramification. So again, this is unavoidable. But other than that, it's the image of a complex cell is a pretty good approximation of a real cell that we are used to. Okay, so that is one definition.
But phi j tilde is just holomorphically bounded. That's it.
Yeah, and it should depend only on x1 up to xj minus 1. So it's it preserves this.
Oh, it's a triangular shape.
Yeah. So that exactly is what preserves this cellular structure, right? So the first cell is just you shift it by a constant. Then the second coordinate you can make a shift depending only on the first coordinate. So you will move the fiber with a shift and so on. So it's exactly this triangular structure that makes it analogous to standard cells.
Therefore, phi j depends only on x1 to xj.
Say again?
Phi j depends only on x1 to xj.
Yeah, I mean, I just wanted to, I just took kind of a general map, but I mean, the definition means that actually the phi j is defined on C, so it takes x1 up to xl, but in fact it depends only on x1 up to xj, and the depends on xj is very simple. Yeah?
Even with V, if you just allow the center to be holomorphic bounded as they are.
You mean in the definition of the complex set? It wouldn't be very different. It's just just a way for us to set things up. So if you wanted, you could define all the fibers with an extra parameter, and kind of then work this into, and then this definition would be somewhat simpler. You would still need the covering maps, though. I mean.
So this would not be covered, right?
I mean, yeah. So you would still, maybe you could avoid this to some extent, but you would still need this, allowing this power. Okay. So I want one. Okay, I'll do it here. So another definition I want is a cover. So I'm going to be thinking about in the same sense that in the real case we do a cellular covering. So we have a space, we want to cover it with cells. Now I have a complex space and I want to cover it with cells. So I'll define what I mean by that. So another definition is that suppose that I have phi alpha are maps from certain C alpha sigma extension to a C alpha to a C with a rho extension. Okay, so I'm going to take a collection like this where alpha is, I don't know, some index. So I have a collection of maps like that, and I'll say that it is a cellular cover. So this is a cellular cover if the union of the phi alpha on C alpha contains C. Okay, so again, this is somewhat more complicated than the real case. In the real case, basically, you just want this. Right, so you're saying, I want cells, and my analog of a cell is the image of a cell under a certain map, and I want this to cover my original cell. But now I'm doing everything with these extensions. Okay, so I want my initial cells to be defined on a slightly bigger cell. Everything should extend to a slightly bigger cell, and the map will go to a slightly bigger cell, and I want the original cell to be covered by the images of these cells. Okay, so it takes some getting used to that. You always have to keep track of this extension, but that is what brings hyperbolic geometry in the picture. I mean, a cell by itself, it doesn't have any good hyperbolic properties. It has good hyperbolic properties when it is embedded in its extension. Okay, so we always have to keep track of this pair, the cell and the extension. All the maps are always defined on some extensions. Okay, so this is what it means to make a cover. So this is exactly what I did in this first exercise. Okay, I wanted I had the disk inside the disk of radius 2. So I had the disk inside the extension. And then I asked you to cover the disk minus the points using extended cells. So I wanted this scenario such that if you extend them, it still maps into this space, and such that their union covers everything. Okay, that's what's written there. So it's exactly an instance of this definition. Okay, and one final definition. So if I have a function, say a bounded holomorphic function L, and I have a map phi from some other cell into C, I'll say that phi is compatible with F if, F composed with phi is identical 0, or F composed with phi is non-vanishing. Okay, so this again is kind of an exact analog of a similar definition in the semi-algebraic case or the minimal case. So in the semi-algebraic case, we usually talk about a cell being compatible with a polynomial. And that means that the sign of the polynomial is constant on that cell. Okay, so here we can talk about the sign because it's complex, but we can talk about vanishing or non-vanishing. So we are saying that a cell is compatible with the function if either the function vanishes identically on the cell or it never vanishes on the cell. Okay, that's the definition.
F belongs to what cube?
This is OB. So this is my notation for bounded holomorphic function.
Okay.
Yeah, just a bounded holomorphic function. Okay, and now with all these definitions, I can give some statement which is analogous to the cell decomposition theorem in the real setting. Okay, so I'll do it here. Questions so far? Okay, so the theorem that we call CPT, so that's cellular parametrization theorem. So we call it parametrization and not subdivision exactly because we have these cells that map into the space. So it's not really a subdivision of a space, it's covering the space by images of maps. So it's more like a parametrization. So I'm going to fix sigma and rho between 0 and infinity. I'll take C rho to be a cell. So what I mean by this is that I have a cell and it has a rho extension, which, as I said, is a non-trivial condition on C. So I just write that this is a cell, but I mean there is a cell with a rho extension. And I'll take F1 up to Fm, Fm to be bounded holomorphic function on this rho extension. Now, this theorem has an analytic version and an algebraic version. So I will state the algebraic version. I'll just say in words what happens in the analytic case. So suppose that C and all of these functions are algebraic of complexity beta. Again, defining complexity exactly, it requires some work, but I mean, think, for instance, about polynomials of degree beta, or semi-algebraic functions that you can describe using equations up to degree beta. It doesn't really matter which precise definition you use.
You don't have to bound the size of coefficients?
No. Yeah, so I mean, yeah, as in the Yom-Din-Gromov lemma, the important thing is that this complexity is only like about the geometric degrees, not about the specific coefficients that you use. Thank you. Okay, and then the claim is that there exists a cellular cover phi 1 up to phi n, where phi j goes from some sigma extension into our cell. So we are covering our cell. So this is a cellular cover. It means that the images of phi j cover C. Okay, so I mean, same definition of cellular cover that I made here, where so one phi j is prepared for every j. 2 phi j compatible with fk for every j and k. Okay, so I'm going to cover my cell, and I'll cover it by cells that are compatible with all my functions.
So in the definition of compatible, non-vanishing means nowhere vanishing.
Yeah, I'm sorry, yeah, nowhere vanishing. I mean, nowhere. Nowhere vanishing. So either everywhere vanishing or nowhere vanishing. So I'm going to cover with cells that are prepared and they are compatible with xj. And finally, the number is going to be less than or equal to some polynomial, depending on the dimension of the cell, in the number of functions, the complexity of the functions, rho, and 1 over sigma. Okay, so if you want to get a first feel for, I mean, you can just think that rho and sigma are fixed. I take them to be the same. I take them to be like 2 or something. Then kind of forget about these parameters. We start with a 2 extension. We end up with a 2 extension. And then what the theorem says is that we can cover using a polynomial number of cells. And it depends primarily on the degrees of the functions and on the number of the functions. Okay, so this is really the kind of getting this polynomial dependence. That's really the hard part, the hardest part of this theorem. That's the part that we couldn't kind of achieve with the standard O minimal method. So the rest of the theorem is quite close to resolution of singularities. I'll explain the sense in which it is close to resolution of singularities. So it's inspired by some ideas from resolution of singularities, but the problem was how to get a good, precise control on the number of cells that you need. And this translates eventually to this good control on the number of charts that you need in Yomdin-Gromov. Okay, so this polynomiality in beta here, that's exactly what was missing. And kind of I will try to show in the next lectures that this polynomiality in beta, it really comes from hyperbolic geometry. So the fact that the cell inside of its extension has a small hyperbolic norm, that imposes a lot of restrictions on the geometry of these cells, and that is what allows us to give very sharp bounds on the number of cells that you need. Okay, so I'll just, I'm almost out of time. I'll just make a few small corollaries. So a corollary which is kind of standard is that if you, so you kind of, in particular, if V is the common zero locus of, F1, Fm inside this cell C, then V is a union of images, images of cells. Okay, so in particular, you can use this theorem to get a parameterization for any analytics or algebraic set, because every cell is either with F identically vanishing or F non-vanishing, so nowhere vanishing. So the cells where one of these F's is nowhere vanishing cannot touch V. And then it follows that V has to be just a union of the remaining cells. And kind of the intuition is that whenever you have a cell compatible with a function, that is kind of like a chart where the function is a normal crossing divisor. Okay, so I'll show that this is true in some precise sense, but that's the intuition, that's kind of the sense in which this is close to resolution of singularities. When we have covered the cell by cells compatible with functions, we have essentially reduced these functions to a monomial times a unit, and and you can take some ideas from a resolution of singularities and try to use them. And I'll show how this can really let you guess some interesting statements in hyperbolic geometry that turn out to be true, just by this analogy. Okay, but I mean, I'm almost out of time, so I'll finish here and continue next time. Thank you.
Thank you. Are there more questions? Comments?
So here in the definition of prepared geometry, I think you're allowing Qj to be 0, right? So you have this parameterization. Can it be negative also, or you're assuming it's no negative?
No, in fact, I'm sorry. I should have said that Qj should be just positive. It should be greater or equal to 1. So it's really only covering maps. It's only to avoid this problem with covers.
So I think I'm missing something. How are you going to cover V by a union of cells which are compatible if it's something smaller dimensional?
So in this case, the cell, one of the fibers would have to be a point. Right? So when I defined the cell, there was the option that a fiber could be just 0, right? So in this case, you would have, so let's say you want to cover, let's say the 0 locus of your function is something like this, then there would be one cell that covers everything here. This would be just disk times a disk, and there would be, in fact, probably covering the whole complement, and then there would be a disk times a point, something like disk O dot star, and this would map into here. And then the map would just, the map would just be exactly the function whose graph I drew here.
Thank you.
More questions?
Could you repeat again what you mean by complexity of an algebraic function?
So I mean, one way is to think that when I said algebraic function, I'm just saying polynomials. Because actually, when you have an algebraic function, you can choose a polynomial whose 0 locus contains this. So you can just say the degree of this polynomial. Another option is to say that, okay, when functions are algebraic, in particular, they're semi-algebraic, and I'm going to take the complexity of their graph as a semi-algebraic set. So just embed everything in R2L, and then you have some semi-algebraic set, and take the complexity here, where here you can define complexity like the sum of the polynomials that you use in a representation of the semi-algebraic set. So I mean, because anyway, everything I state is just some polynomial, any reasonable notion of complexity that you use will give you roughly the same thing. You just need the two complexities to be polynomially depending on each other. So.
Any idea of the degree of this polynomial?
What do you mean, any idea of the degree of this which polynomial?
Number 3.
Here?
Yeah.
What is the polynomial? That is quite, I mean, it's completely explicit. So if you follow the proof, which is 100 and something pages, then you would see what it is. But we didn't try to. I think it would probably be doubly exponential in the dimension. So that's how it usually works in this semi-algebraic complexity. It's usually doubly exponential. So that's what I expect.
In these cells, you control explicitly all the derivatives at once, yeah?
Well, I mean, in the cells, what you have are holomorphic maps. And for holomorphic maps, it's not exactly that you have let's say you have an annulus. Then it's not exactly that the derivatives are bounded. If the annulus is very long, it could have big derivatives. But still, the Laurent expansion, you can control the rate of convergence. So if you have a bound on the function in an extended cell, then you know that its Laurent expansion converges in the original cell with known rate. So I mean, it's similar to controlling all of the derivatives, but.
Okay.
So I think you said for your theorem, you have also a version when things are not algebraic but analytic.
Yeah,
And
sorry.
you say something about it.
So basically, it's kind of just a simpler statement. So here I said exactly what is n, right? I said n is bounded in terms of the complexity. If you just take a cell which is analytic, then there would exist such a covering. And if you let this cell vary in a definable family in an O-minima structure, then this n would be uniformly bounded over the family. Okay, so I'm saying if you have any kind of collection of cells and functions and it's in a definable family, then you can make such a covering and the number of cells that you need will be uniformly bounded. And when it is actually algebraic, we can even say what the number would be. It would be polynomial in the degree. Yeah, I think Mikhail had maybe. It was the same one. Okay.
Okay, so any further questions? So, so let us thank Gal again.
Okay, thank you.